are discussing the armature induced EMF on load. So the topics to be covered are the first, the rating of the synchronous generators, why it is in kVA and not kilowatt. Then we'll discuss the armature EMF on load and on no load and on different types of load, and different voltage drops on load which has to be considered to calculate the terminal voltage. So the ratings of the synchronous generators, it is given in kVA. Now why it is that usually the electrical machines are rated in the kilowatts and not kVA, because they carry the load without overheating and damaging the insulation. So the rating of electrical machines is governed by the temperature rise, and that is caused by the internal losses in the machine itself. And the temperature rise is the I square R losses, and different losses whatever is taking place, that gives rise to the temperature, and therefore the type of insulation is also used in the motors depending on the temperature which it can go up to without any deterioration in the insulating materials. So the copper I squared loss in the armature basically depends on the magnitude of the current flowing through the armature conductors, and the core loss depends on the operating voltage. If you remember the lecture before, we had discussed about the core loss, hysteresis loss and the eddy current losses, and its equation which was mainly dependent on the operating voltage, and the I square R losses because the armature resistance is very less, because we use thick conductors for it, so the resistance of the armature conductors will be very less, but the current flowing will be of very high magnitude. So I square R losses are there in the armature of the synchronous generators. But both of these losses are independent of the power factor. Therefore, the power in kilowatt is proportional to the power factor, because the power is given as VI cos phi. VI cos phi, where cos phi is the power factor of the load, and cos phi will be dependent on the load what you are connecting it. If it is an inductive load, the power factor will be less than 1. Whether it is capacitive load, still it will be less than 1. Only thing is that in inductive load, the current will be lagging the voltage. For capacitive load, the current will be leading the voltage. But when the power rating is in kilowatt, this means we are taking the power factor of the load into consideration. Now, for example, if an alternator is rated at 1000 kVA at full load, and suppose it delivers power to different loads at different power factors. So if the power factor is 0.4, it will deliver only 400 kilowatts. If the power factor changes to 0.6, it will deliver 600 kilowatts. So and so on. So if the power factor is 1, it will deliver the maximum load, that is your 1000 kilowatts when it is rated for 1000 kVA. So at these loads, current supplied by the alternator will be the same, and the losses will also remain the same. Therefore, the rating of an alternator depends on the maximum current it can deliver without overheating, and the voltage for which it is designed. Therefore, the power factor of the load is not considered to give the rating of the synchronous generators or the alternators, and therefore the synchronous generator or the alternators are rated in kVA and not in kilowatts. So this is the reason why these generators are rated in the kVA. So what do you conclude? Because these generators are independent of the power factor, therefore the generator rating is in kVA and not kilowatt. Now armature EMF on load. So the armature induced EMF E0, that was on no load, which we had discussed earlier, and EA is the EMF induced by the armature field. So the net EMF will be E is equal to E0 plus EA. At no load, your armature EMF will be equal to 0, and so the flux is 0, and therefore E will be equal to E0. Okay, because when the load is 0, the armature current will be 0. If the armature current is 0, there will be no field produced by the armature conductors, and therefore the net induced EMF by the armature will be equal to only the no load EMF, that is the EMF induced due to the main field flux. So E will be equal to E0. Now the armature EMF with non-inductive load, that means it is a resistive load, so the power factor is unity, and the armature will produce a flux which is lagging behind the main field by an angle 90 degrees, which we had discussed earlier also. So over here we are talking about the induced EMFs. So the induced EMF in the armature will lag behind the actual induced EMF by the field by 90 degrees. Like EA is lagging behind E0 by 90 degrees. So the resultant will be the phasor sum of EA and E0. That is the armature induced EMF and the no load EMF, and E will be the final EMF. Now the armature alternator EMF with inductive load. For a pure inductive load, the alternator current flows through the armature current which lags behind by 90 degrees. Now when the current lags behind E0 by 90 degrees, EA will again lag behind the armature current by 90 degrees because the induced EMF will lag behind its flux by 90 degrees. So these two fluxes, the main flux and the armature flux, are in just opposition, so it will tend to reduce the actual induced EMF, and E will be equal to E0 minus EA. Now for the capacitive load, it will be just the opposite. The current in the armature conductor will lead the induced EMF by 90 degrees, so it is in the same direction as the field MMF, and therefore the two flux are supporting each other, and therefore the induced EMFs will be also additive in nature. So the induced EMF E will be equal to E0 plus EA, that is the no load EMF plus the armature EMF. Now when we consider the armature reactance, E0 is always in quadrature with the load current and it is proportional to it, and it resembles, now armature reactance is similar to the inductive load. So due to the armature reactance, the phasor will be the same as the inductive load, and therefore the XA will be given as EA by I, where XA is the armature reactance, armature reaction reactance. So when you have alternator on load, now what will be the different voltages? So when the armature is on no load, there will be no current in the armature winding, and if there is no current in the armature winding, there will be no rotor no armature MMF being produced. But as soon as you load the alternator, a current starts flowing in the armature of the alternator, and therefore the MMF, our magnetic field, will be produced by the armature currents. That will be a rotating magnetic field because it is a three-phase current system. Armature is a three-phase AC system. Therefore, it will produce a rotating magnetic field in the air gap, and therefore your air gap flux is changed from the no load condition, because under no load condition this field was equal to 0. So as the load on an alternator is varied, its terminal voltage will also change, and this variation in the terminal voltage is due to the voltage drop due to the armature resistance, which is very small because RA is almost negligible armature resistance. The voltage drop due to the armature leakage reactance, that is all the flux is not passing through the produced by the armature is not passing through the field, that is your leakage reactance, and the voltage drop due to the armature reaction. So all these voltage drops we will first consider one by one and then combine it. So what is the armature resistance? The armature resistance, actually when we talk about the resistance, basically it is the DC resistance, and DC resistance is measured by supplying the DC voltage and the current, and you measure the resistance by R is equal to V by I. But the AC resistance is more than the DC resistance due to the skin effect, and so normally we take the ranges for the AC resistance to be 1.25 to 1.75 the DC resistance times the DC resistance. So the armature resistance drop will cause a voltage drop of IRA, which will be in phase with the armature current because it is a resistive drop, and practically many a times we neglect this resistance drop because RA is very small. The armature resistance is very small, normally in the range of 0.1 to 0.1 maybe less than 0.1 also, it may be 0.05 ohms per phase. So heavy copper loss, but heavy copper loss occurs in the machines because of this small armature resistance also. Now we will consider the armature leakage reactance. When the current flows through the armature current conductors, the local fluxes are set, and this flux will be linking the armature winding along with the field winding. So this is the figure where we can understand what is the leakage flux. So now over here you can see the armature conductors, and it is having a double layer winding. So we have shown two conductors. Then you have got the rotor, and in between you have got the air gap. So whatever flux is being produced by the rotor has to link to the armature conductors after crossing this air gap, and whatever flux is produced by the armature conductors has to link with the field through this air gap only. So we have got different types of leakage inductances, that is your slot leakage flux, then the leakage flux in the end connections, and the air gap leakage flux. So what is the slot leakage flux? The slot leakage flux is the flux which surrounds the armature conductors embedded in the iron or placed in the slots but does not pass through the air gap, is called the slot leakage flux. Air gap leakage flux, the flux which surrounds the armature conductors and passes through the air gap and is called the air gap leakage flux. So it is crossing and it is cut by the rotor conductors. End connection leakage flux, the armature winding has got an overhanging at the ends of the stators outside of the core, and that is known as the end connection leakage flux, and that is also called as overhang leakage flux because the armature conductors are beyond the stator core, and so it is like an hanging part of the armature windings. Now armature leakage reactance drop. The total leakage flux which links the armature winding gives rise to the inductance, and we have already studied about the armature reactance, which will have a behavior similar to the inductive load, and the inductance is given by phi n by I. You all know the formula, where I is the leakage, I is the current, and phi is the leakage flux in Webers, n is the number of turns. So the inductance L when multiplied by omega gives us the leakage reactance, and the voltage drop which occurs due to this leakage reactance will be given as voltage drop in the this voltage will be in quadrature because it is like an inductive drop, so it will lag behind. And so the phasor diagram you can see over here, the IARA drop is in phase with the current, while the IAXL drop, that is due to the leakage reactance, is in quadrature, is at 90 degrees to the main armature current, and this is your total induced EMF. So a part of the generated EMF is used in overcoming this reactance EMF, and E will be given as V plus I into RA plus JXL. Now what is the armature reactance drop? Armature reaction, as I told you, it will be similar to the reactance drop. So the load is generally inductive, and the effect of armature reaction is also to reduce the generated voltage, because most of the loads what you have got in your home, they are not capacitive in nature but they are inductive in nature, and so that is the most popular form of the load, and we'll try to analyze the armature reaction due to that inductive load. Since the armature reaction results in a voltage effect by the change in the flux produced by current in the same circuit, and its effect is of the same nature as the inductive reactance. Therefore, armature reaction effect is accounted for by assuming the presence of a fictitious reactance XAR in the armature winding, and the quantity XAR is called the reactance of the armature reaction because it is not physically present, but due to the load it appears in the system. So the value of armature reaction reactance is XAR, and the drop will be IA into XAR. Therefore, you can see that there will be different voltage drops in the given alternator and the voltage will vary as per the load connected to the alternator. So what we have discussed today is the why the rating of the synchronous generator is in kVA, not in kilowatts. Then the armature EMF, the behavior of the armature EMF on load and on different types of the load, on no load and different types of the load, and different voltage drops on different types of the load.